Hello everyone, today let's solve Leetcode 968 binary tree cameras. Here, given the root of a binary tree as input, we need to find the minimum number of cameras required to monitor the entire tree. Knowing a camera placed at a node covers itself, its parent, and its immediate children. For example, if we place a camera at node B, then it will automatically cover itself, its parent node A, and its immediate children C and D. So in just one camera, we are able to cover this entire tree. But suppose instead of placing the camera at node B, we place it at root node A. In that case, it will only be covering the node A itself and its immediate child B. But this camera will not be able to cover the other two nodes C and D. So for covering C and D, we will need two extra cameras which will cover these two nodes individually. So in this case, we can see that we are using three cameras to cover the same binary tree which we have already covered previously using one camera. So depending on the placement of cameras, the number of cameras used to cover the entire tree will differ. And we have to return the minimum number of cameras in which we can complete this task. For this example, it will be 1. But how will we ensure that every time we do the optimal placement? We can think of two primary ways to approach placing the cameras. One is from top to down, another is from bottom to up. So we have this example and we start placing the camera from the top. So suppose if we place a camera at the very first node, then it will cover this node and its next child, this one. So obviously for the third node, we will need another camera, right? But is it the optimal one? It is very obvious that this is not the optimal result. We know that we can easily cover these three nodes using a single camera. Now suppose while going top down, we decide that we will not place a camera at the first node. Instead, we will defer it. Say, suppose we don't place a camera here, then we have to move to the next level and then place a camera. By placing this camera, this node itself is covered as well as its parent and its child. All the three are covered. So in this case, you may think that it is working, but it's not. Suppose in this example, there was another level in which there were two nodes, which were the child of the third node. And if we don't place a camera at this level, the next level is not covered. So we definitely need to place cameras at the next level. So we place cameras here at both the nodes. And you can see that again, the same thing is happening. Only two cameras at this point and this point would have been enough to cover the entire tree. But as we are going from top down and we don't know the details of the further nodes, so we are making like premature decision of not placing a camera here, and that's why we are not getting the optimal result. So we can see that the top down approach will not necessarily give us the minimum number of cameras. Top down means simply pre-order traversal here. So if we do a pre-order traversal, we will be processing the current node before processing the children. So that will not work. And if we do bottom up approach, what we will do is we will first process the children, get their status, and then accordingly process the current node. Bottom up is actually the post-order traversal. So let's try placing the camera from the bottom up. Now consider the leaf node. Do we really need to put a camera here? I don't think so. Instead of the leaf, if we put one camera at the parent of the leaf, the single camera will automatically cover the leaf as well as its sibling. So what we are doing here is we are deferring the placement of the camera until it's absolutely needed. So we'll simply place a camera here. After placing the camera at this node, we can see that its parent, this node is already covered. So we don't need to place any camera here, and we can move upward to the root node which is not covered and place a camera there. So only in two cameras we can easily cover the entire tree. Similarly, for this example, we will again not place any camera at the leaf node and we'll move to its parent, and then we will place the camera. So after placing this here, all the three nodes are covered. So this entire tree ends up being covered with just one camera. And by placing cameras from the bottom, we arrived at the minimum result very naturally in both of these examples. The bottom-up or post-order strategy works here because we delay placing a camera until it's absolutely needed. This gives each node a better chance to get covered by its parent, which pushes cameras as high as possible in the tree where they can cover more nodes. So the rule we are following is pretty simple. A node places a camera only when one of its children is uncovered. Otherwise, it defers placing a camera and lets the parent handle it. This means the camera placement at any node is determined entirely by the coverage requirements of its children and not by the node's own needs. And this leads us to define three possible states for any given node. The first state is has cam. That means the node has a camera like this one, and it covers itself, its parent, as well as its children. The next state is covered. This means the node is covered by a camera from one of its children, but it does not have a camera itself. As we are moving bottom up, so we are considering the coverage from the children here to be clear. The third state is needs coverage. That is, the node is not covered and it demands a camera from its parent, like this one. See, this one is already covered by the camera from this node, but the node at the top here is actually not covered. That means it needs a camera. But will we place a camera instantly? No, we will not. We will defer the camera placement to its parent. So what we will do, we will not place the camera here, but we will wait and check what happens to its parent. Suppose if there is a parent here, when we reach the parent, we will simply go and place the camera here. The reason is it will increase the coverage as it will cover this node along with the current node and one level above. So in all those cases, we will keep the status of the current node as needs coverage. This works, but there is an edge case, that is the root node, which we can easily see in this example as well. As we run DFS from the root, we must check what is the status of the root after the entire DFS completes. And in this case, the status of the root is needs coverage. And it means the entire tree below it is monitored, but the root itself is not monitored, as it was depending on its parent for coverage. But note that the root node does not have any parent. So in this single case, for the root node, we need to add one extra camera. So this is one edge case we need to cover. Apart from this, the entire algorithm will work easily. Now let's quickly see how we will assign the states at each node. I have added a decision table which shows all the possible combination of states for the left and right child. You don't necessarily need to come up with the entire table to solve this problem, but this will help you to understand the different cases better. When we traverse a node in post order, we use the status of its left and right child to determine the status of the current node. Suppose we have 3 nodes and this is the current node. So if any of the left or right child needs coverage, that is, here you can see that in all these 5 combinations, at least one of the left or right child has their status as needs COV. So in this case, what should we do? We will definitely need to give the current node a camera, right? So if any of these 2 nodes needs coverage, then we obviously have to give a camera to the current node. Then only we will be able to cover its left and right child both. Because as we are moving in bottom up fashion, so if any node says I need coverage, means it's expecting coverage from its parent node. So on reaching the parent node, we definitely need to assign a camera. And with this one observation, we have already checked more than half of the combinations. Now in the remaining combinations, the remaining word is important here. If in the remaining combinations, we see that any of the left child or right child has a camera. So say this is the case where at least one of them has a camera. So obviously if this child has a camera, it will be covering its parent as well, right? That means our current node is already covered and we don't need to put any camera here because it is covered with the help of the camera from its child. But the point to note here is that in the previous set also, we had a few combinations with has cam. But the other child status in such combinations was needs coverage. So we had to give priority to the coverage needed and assign camera to the current node in all such cases, even if one of the child was already having a camera. So that's why we are giving a camera in the first set. But in the second set, we are already excluding all the cases that were part of the first set. In the second set, as no combination has needs coverage, so if any of the child already has a camera, we can safely set the status of the current node as covered. Now, after finishing these 2 sets, there is one last combination left, where both the left and right child have their status as covered. Suppose this is a small tree, where this is the left child and right child, and both are having status covered. What does this mean? This is the current node. This means that both the child of the current node does not have any camera of their own, and they are relying on their children to provide them coverage. That means there is a camera here which is actually providing coverage to this node. And this coverage cannot extend to our current node, right? In that case, what will happen? Our current node is actually not covered. It's in not covered state and it needs coverage. And to give it coverage, what we can do, there are 2 ways. One is to give a camera directly here, and second is to defer its camera requirement to its parent. So what is the better way? So if we give a camera here, then this camera will give double coverage to the already covered children, which is not optimal, right? So what we will do? we will try delaying the camera placement. And so we are actually not providing camera here. We'll set the status as needs coverage and we are deferring the camera placement to its parent. So these are all the three cases that we need to check while taking the decision of camera placement at each node. And this we will do using our bottom-up solution, which we can simply implement using a greedy post-order DFS, which simply means while traversing, we will process the child nodes first and then process the current node. As we are visiting each node only once, so the time complexity is just O of n, where n is the number of nodes. And the space we are using is just the recursion stack, which grows with the height of the tree. So the space complexity is O of h, where h denotes the tree height. So if you have already understood the approach, then the code is going to be very simple. Initially, let's define three status constants as we discussed. First is has camera. Let's assign it 1. It means that a node already has a camera. Next is covered. Let's assign it number 2. That is the node is covered by its child. And the third one is needs coverage. And let's assign it 3. This means the node is not covered and needs coverage from its parent. Now let's take our result variable, which will be the minimum number of cameras. So let's assign cameras to 0. So now let's define our DFS function. So def DFS, it will take a node as input and return an integer value as its status. Now let's say if the node does not exist, that is if not node, then we can simply return that it's covered. As if a node is not present, that means it does not need a camera as well as it does not need coverage. So we can safely say that null nodes are automatically covered and return covered as the result. Now once we have handled the null nodes, now it's time to do the main DFS processing. Before processing the current node, we will process its children. And this is the greedy approach, as we are deferring the camera placement decision as much as possible. So this is actually greedy post-order DFS. So in post-order, we first recurse on the left and right child and then process the current node. So let's recurse on the children. So left child status is equal to DFS of node dot left. And similarly, we will store the right child status from the DFS of node dot right. So now once we have both the status, it's time to process the current node. There will be three cases that we discussed, which we will be checking here. First is if any of the child needs coverage, we have to place a camera at the current node. So if left child status is needs coverage or right child status is needs coverage, then we will simply increment the number of cameras and return the status. But note that the cameras variable is not a local variable to this DFS function. So that's why we will first mention that cameras is a non-local variable to our DFS function here so that it's accessible inside this function, and then increment it. So cameras plus is equal to 1. So this means we are assigning a camera to the current node in this case. So we will return has cam as the status. So case 1 covers all these 5 combinations as we discussed previously. The next case is, apart from case 1, if any of the child already has a camera, then we can say that the node is already covered. So if left child status is has cam or right child status is has cam, in that case we can simply return covered as the status of the current node. Now if a node does not fall in these two cases, that means the node is not covered and we need to return needs coverage as the status. Now after defining the DFS, we also need to call it. We will run DFS on the root node. But there is one edge case that we already discussed. So if DFS of root returns its status as needs coverage, in that case we will be returning one extra camera, that is cameras plus 1. Otherwise we can simply return cameras as the result. So what is happening here is, if the root node is not covered and expects or needs coverage from its parent node which is not present, so we explicitly add one camera for the root node and we will return cameras plus 1 as the result. But if the status of the root is anything else other than needs coverage, means it is already being monitored. So we directly return cameras as the result. So let's run it. You can see that this is accepted and is working fine. I have added the entire solution on my website DKodeTree.com. Feel free to check it out, and I have linked it in the description and on pinned comment as well. If this was helpful, do hit the like button and subscribe to DKodeTree for more such videos. Till then, keep preparing and I will see you in the next one.